This would be a rising or positive edge triggered one-shot, and essentially does exactly what the name suggests, and that the one-shot function is only enabled once for a period t on a rising or positive going transition of the controlling input. Alternatively, a negative or falling edge triggered one-shot is one that the one-shot function is only enabled once for a period t on a falling or negative going transition of the controlling input. One-shots can be used to assert an output for a desired time period following the energized or de-energized transition of another device. One-shots are particularly interesting because manufacturers occasionally include a slew of handy features, including resets and retriggerable versus non-retriggerable one-shots. Note, for this general purpose orientation, I've purposely simplified the timing diagram for rising and falling edge one-shots. Finally, compare this behavior to a timer executing the cumulative on-delay function. A cumulative on-delay timer is a record-keeping function where the timer does not temporarily shift the outputs, but rather keeps track of how long its controlling input has been energized. Only after the controlling input has been asserted for the predetermined period of time do the outputs respond. Note, despite the controlling input being discontinuously energized, only once the timer has accumulated the required delay period here do the contacts switch to their activated opposite states. Such a timer could be used to keep track of how long a particular controlling input has been asserted, and then alert the system that some maintenance or other task must occur. I like to think of cumulative on-delay timers as little accountants that keep track of how long the controlling input has been asserted and continually monitor how much time remains in the bank before it activates the output. Note, for this general purpose orientation, I've purposely simplified the timing diagram for cumulative on-delay timers. To be sure, there are other timer functions and twisted offspring of unholy unions of these common functions. However, these are more than likely the most common timer functions you'll run across. This orientation is intended to be general in nature and does not dive into specifics nor manufacturer idiosyncrasies. Be aware of subtle differences in different terminology used to describe the same features. Long story short, RTFM. The classic introductory example of an on-delay timer is the time-shifted response of pilot lights. Note the 3-wire control circuit in rungs 1 and 2 serves to simultaneously energize the coil of a regular control relay, CR1, and the coil of a timer relay, TR1. Contact CR1A associated with the regular control relay serves only as a holding contact, allowing the circuit to maintain the last asserted state. Rung 3 contains a normally closed time-open contact TR1A associated with timer relay. Rung 4 contains contact TR1B, a normally open time-closed contact associated with the timer relay. Let's assume the timer executing the on-delay function is set to execute a 5-second delay. Note the start state of this circuit is red light on, green light off. When an operator presses the start push button, both the coil of control relay CR1 and timer relay TR1 are energized. Contact CR1A immediately switches to the activated closed state and establishes a holding circuit. An operator can release the start push button. In contrast, the on-delay contacts associated with timer relay TR1 do not immediately change states. TR1A remains closed and TR1B remains open. The red light remains on and the green light remains off, only after the predetermined delay period of 1, 2, 3, 4, 5 seconds has elapsed do these on-delay contacts change states. TR1A opens and TR1B closes. The red light turns off and the green light turns on 5 seconds after the controlling input was energized. When an operator presses and releases stop, both control relay CR1 and timer relay TR1 coils are de-energized, and all associated contacts immediately return to their deactivated state. CR1A opens, removing the holding circuit. TR1A closes. TR1B opens. The red light is on. The green light is off. We have returned to the start state of our system. Again, note the timer relay delayed the transition of the associated contacts, and thus the response to the pilot lights for a period of 5 seconds after the start button was pressed. Note, if an operator were to press and release start, and then immediately press and release stop prior to the delay period elapsing, the timer would clear and reset. Consider this slightly modified circuit, further illustrating this fact. Note we've ditched the regular control relay CR1 and the holding contact CR1A. CR1A has been replaced with TR1H, yet another normally open time-closed contact associated with the timer relay TR1. Let's assume the on-delay period is again set to 5 seconds. If you truly understand the behavior of an on-delay timer, you should be able to predict how this circuit works given the following two scenarios. First, when an operator presses and immediately releases the start push button, and 2, when an operator presses and holds the start push button closed for a period of longer than 5 seconds. By all means, pause the lecture and think about this. If you're tracking, here's how the circuit responds to the first scenario, when an operator presses and immediately releases the start push button. Long story short, it doesn't. If an operator presses and releases the start push button, the coil of the timer relay is only momentarily energized, and when energized, starts initiating the 5-second countdown. However, the moment the operator releases the start push button, the coil of timer relay TR1 is de-energized and the countdown is reset back to 0. The second scenario is different. Only when an operator presses and holds the start push button for a period of longer than the predetermined 1, 2, 3, 4, 5 seconds do the associated contacts change states. TR1H, the holding contact, closes and establishes the holding circuit. Additionally, TR1A opens and TR1B closes. An operator can now release the start push button. The red light is off, the green light is on. The difference being an operator had to be patient enough to press and hold the button for a period of 5 seconds, thereby giving them a full 5 seconds to contemplate if this is really what they mean to do. The stop button serves to de-energize the coil of timer relay TR1 and thus return the system to its start state. Red light on, green light off. I think this is a pretty fun example circuit that illustrates not only the function, but also the utility of on-delay timers. Note this particular circuit required the timer relay coil be continuously energized for a period of 5 seconds before the lights flip-flopped and the holding circuit was established. We'll examine another function called a cumulative on-delay timer in later lectures that maintains a running tally of elapsed time despite discontinuous assertion of the controlling input. Besides making some stupid lights blink, a timer relay can also be used to perform synchronization of separate industrial tasks. For example, consider an electrically controlled hydraulic system that must extend cylinder A on demand, then after a 5-second dwell period, extend cylinder B. The ladder logic controlling this circuit might look something like this. The 3-wire control circuit in rungs 1 and 2 serves to energize the coil of a regular control relay CR1 and the coil of a timer relay TR1. Contact CR1H associated with a regular control relay serves as a holding contact, allowing the circuit to maintain the last asserted state. Note the inclusion of a maintained E-stop that serves to de-energize the whole system. Rung 3 contains a regular, normally open contact CR1A associated with a regular control relay CR1 in series with solenoid A. Rung 4, in contrast, contains a normally open time-closed contact TR1B associated with timer relay TR1 in series with solenoid B. Note CR1H, CR1A will respond immediately, whereas TR1B will do so only after the delay period T has elapsed. When an operator presses the start push button, the coil of CR1 and TR1 are both energized. The contacts associated with control relay CR1 immediately change states. CR1H closes and establishes a holding circuit, allowing an operator to release the start push button. CR1A closes and energizes solenoid A. DCVA shifts to the straight-through position, and cylinder A extends. TR1B, in contrast, does not immediately change to its opposite state, but rather remains open, and solenoid B remains de-energized. Once a 1, 2, 3, 4, 5-second delay has elapsed, the normally open time-closed contact TR1B closes and energizes solenoid B. DCVB shifts to the straight-through position, and cylinder B extends. In this scenario, the cylinders would remain extended. Note that the accumulator and check valve on the pressure line leading to DCVA ensures that while cylinder B is in the act of extending, it does not interfere with the force exerted by cylinder A. This additional directional control valve is intended to provide a means of safely discharging the accumulator in the event the system needs to be serviced. Additionally, note our pump is a pressure-compensated variable displacement pump that de-strokes to 0 gallons per minute at the firing pressure, conveniently set that below the main pressure relief valve. The high-pressure standby mode of the pressure-compensated variable displacement pump thus keeps the main pressure relief valve closed and allows both cylinders A and B to exert continual force at the limits of travel. Sorry for the side trip to hydraulics land. Ordinarily, I try to stick to exclusively electrical control topics or exclusively hydraulic topics, depending on the focus of the particular lecture. However, I do sometimes succumb to temptation to mix the two. Those individuals interested in parallel hydraulic circuits, accumulators, and pressure-compensated variable displacement pumps, and more are encouraged to check out the Hydraulics and Electrical Control of Hydraulic Systems playlist available at the Big Bad Tech channel. If an operator were to press and release the stop button, both control relay CR1 and timer relay TR1 coils are de-energized and all associated contacts immediately return to their deactivated state. When CRH opens up, it removes the holding circuit. When CR1A opens, it de-energizes solenoid A. When TR1B opens, it de-energizes solenoid B. Both spring offset directional control valves shift to the cross-connect position, and cylinders A and B retract. We've returned to the start state of our system. Again, note the contacts associated with the regular control relay, CR1H, CR1A, responded as soon as control relay CR1's coil was energized, whereas the contact associated with the timer relay, TR1B, responded only after a period of 5 seconds after timer relay TR1's coil was energized. Note we can modify our existing electrically controlled hydraulic system to include additional functionality. On the hydraulic side, we've included a limit switch on cylinder B. Limit switch B senses when the rod makes contact at cylinder B's limit of extension. On the electrical control side, the normally closed side of limit switch B takes the place of the stop button. The behavior of this system is essentially the repeat of the previous example. However, upon an operator pressing and releasing the start button, the system performs a complete sequence and returns to the start state without an operator's continued involvement. Allow me to demonstrate. When an operator presses start, CR1 and TR1 are both energized. The contacts associated with CR1 immediately change states, whereas the contact associated with TR1 begins a 5-second countdown. The closure of CR1A shifts directional control valve A to the straight-through position, and cylinder A extends. After a delay period of 1, 2, 3, 4, 5 seconds, TR1B closes and energizes the solenoid of directional control valve B. Directional control valve B shifts to the straight-through position, and cylinder B extends. When cylinder B strikes limit switch B at the limits of travel, limit switch B opens and de-energizes CR1 and TR1. All associated contacts immediately return to their deactivated state. CR1H opens and removes the holding contact. CR1A opens, de-energizing the solenoid of directional control valve A. TR1B opens, de-energizing the solenoid of directional control valve B. The spring offset valves return to their deactivated cross-connect position, and the rods retract. Note when rod B retracts from the reset region of limit switch B, the normally closed side of limit switch B recloses and returns us to the start state of our system. Again, note the contact associated with the timer relay, TR1B, responded only 5 seconds after timer relay TR1's coil was energized. This circuit could be used to clamp and press an object for a period of 5 seconds with cylinder A prior to being punched or bent by cylinder B. The limit switch ensures the system returns to the start state only after cylinder B has completed the required travel. The substitution of the normally closed limit switch in place of the normally closed stop push button therefore allows the system to automatically execute a complete one-cycle reciprocation, including a dwell period, at the touch of a single button. Moving on, timers are not exclusively used in electrically controlled hydraulic systems, but can also be used to coordinate the activity of electric motors. Consider a simple motor-driven conveyor belt system with 2 sections, A and B. At the start of the day, both belts are empty, and then a production line starts dropping boxes onto the far end of belt A. Given boxes only get on the belt at the very far end of A, and belt B is empty, it'd be kind of wasteful to spin section B until something was placed on it. Given it would take a predictable amount of time for a box placed at one end of A to reach the other, conveyor belt B could delay starting a time period after belt B has been energized. This sounds like a perfect application for an on-delay timer. The ladder logic coordinating this simple system might look something like this. The 3-wire control circuit in rungs 1 and 2 serve to energize the coil of contactor A and the coil of timer relay TR1. Contact A1, an auxiliary contact associated with contactor A, serves as a holding contact, allowing the circuit to maintain the last asserted state. Rung 3 contains a normally open time-closed contact, TR1B, associated with timer relay TR1 in series with the coil of contactor B. No overloads for motor A and motor B are in series with one another and serve to de-energize the whole system if one or both overloads detect a sustained overload condition. Additionally, note the maintained E-stop serves to de-energize the whole system. When our operator presses and releases the start button, the coil of both contactor A and timer relay TR1 are energized. Contactor A closes and belt A springs to life. Note A1, the auxiliary contact associated with contactor A, immediately responds and establishes a holding circuit. This allows an operator to release the start button. TR1B, in contrast, remains open because the timer relay TR1 is still counting down the delay period. After the predetermined period of time has elapsed, the normally open time-closed contact TR1B closes and energizes the coil of contactor B just as the box tumbles onto belt B. Contactor B closes and motor B springs to life, ushering the first box placed on belt A along to its intended destination. As can be expected, an operator pressing and releasing the stop push button would de-energize both contactor coil A and B, as well as timer relay coil TR1, and return the system to its original start state. Note, as currently implemented, this system only bases the decision to start belt B on time, not reality. If the system was started with a box located in the middle of belt A rather than the far end, or stopped in mid-travel and then started again, the box would reach belt B sooner than expected. Add to this the nightmare scenario of box after box piling up at the transition point and spilling onto the floor. An especially dangerous scenario if you happen to be making scorpions at a scorpion factory. Long story short, this example is not meant to be a robust or proven industrial application, but rather familiarize the viewers with the advantages and notable shortcomings of on-delay timer applications. Expect us to revisit similar applications in later lectures, allowing for smoother transitions and more desirable performance. Alright, that is that for this lecture. I was going to dive into on-delay timers coordinating reduced voltage starters. However, I think I'm going to hold that off for another entire lecture, since it comes with some associated baggage, notably an understanding of reduced voltage starters. If you are equipped for this journey, by all means proceed to the reduced voltage starters using timers lecture, but if not, here's a preview. The most basic application of on-delay timers is for scenarios in which one or more contacts must open or close a measurable time period after an input has been asserted. Recall that primary resistor, part winding, and Y-start delta run reduced voltage starters are all characterized by two distinct stages, start and run, and they necessitate a reconfiguration during the transition. Additionally, some types of solid-state soft starters, specifically those that are AC53B rated, must be bypassed during the run stage and given a chance to cool. All these applications are perfectly suited for on-delay timers, a timer function that delays the transition of associated contacts a predetermined period of time after the controlling input has been asserted. By all means, check this lecture out if you've got the time. Pun intended. In conclusion, this lecture took a brief look at timers and the on-delay function. We learned the difference between single and multifunction timers, discussed the methods timers use to determine delay period, compared and contrasted general timer functions with one another, learned how to set up an example timer to perform the on-delay function, and finally employed a timer executing the on-delay function in several illustrated examples. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.